5 minutes, sir. Still some people are joining.
Please, not an issue.
Good evening, one and all. Good evening, sir. We are very pleased to welcome you, sir, to this fourth day of the 2-week faculty development program, sir. Thank you, sir. Yes, sir. You can start the session, sir.
Good evening to all of you. Can you hear me?
Yes, sir. We
And,
can hear, sir.
and you can see the presentation?
Yes, sir.
Okay. So today, my focus will be on computing, especially in the scientific domain. What are the issues when it comes to computing? What are the issues when it comes to computing applied to different class of problems? We will be focusing on problems relevant to hydrodynamics, but not really restricted to only hydrodynamics. It will be slightly focused on major issues by which can actually improve the performance of computing in general. Now, before we start, let's get few basic issues right. One is, why do we need computing? That's the first question engineer should ask. There was a time when things were computed, calculated analytically. Then, with the help of machines, people started computing, that is called mechanical computing with machines. Then, with advancement in numerical mathematics, advancement in computing power, that is CPU, advances in visualization, all combined together gave rise to the field of scientific computing. Now, there is a famous example of Turing machine. Whatever you can do with any modern computer, the same can be done by Turing machine. That helps you in analyzing the complexity. That what is the level of complexity in your computing process. So when it comes to time, when it comes to the power, the memory, they're all related to roughly the complexity. So we need to understand, do we really need complex algorithms? If you need, where do you need them? In the field of engineering, in the field of hydrodynamics, what kind of problems are there where really high performance computing is needed? Most of the time, we take a problem and apply it to whatever we know without really understanding, do we really need that kind of computing power to solve a problem? For example, there are cases where you do not have dominance of viscous effects. And if you do not have dominance of viscous effect, then you really don't need the Navier-Stokes equation. You can actually solve them using potential flow. But still, people will use Navier-Stokes equation even when they are not really needed. Similarly, you have class of problems where closed form solutions are available. There you don't need numerical analysis. You need numerical analysis only when the closed form solutions are not available or when they are too hard to be computed. There are advantages of scientific computing, there are disadvantages of scientific computing. Advantages are that it reduces your reliance on experimental analysis. It also reduces your reliance on high class mathematics. When I say high class mathematics, means mathematics which is really understood by only a few group of people. That's the problem with closed form solutions. So today we'll be briefly touching about all these issues. The first is the introduction, the outline of the lecture. Then what are the software issues? When it comes to improving the performance of scientific computing, what is the role of parallelization, how do we focus on parallel computing, what are the hardware issues. Now, assume that you are dealing with a class of problems where viscous effects are dominating. You have a body which is running in water. The speed of the body is high, and you are looking for drag. Now, for the same problem, if we say that we are looking for thrust, then the viscous effect will not dominate. So, any problem of thrust computing, for example, thrust delivered by propeller, they can be solved by using potential flow. That's where the panel methods comes into picture. Quadratic panel method, cubic panel method. They have been very successful for computing the added mass because it is not really dependent upon the viscosity. So if viscous effects are not important, then rely on potential flow. Very fast, not really complex as far as the numerical analysis is concerned. But assume the viscous effects are dominating, for example, drag, speed is very high, or you want to see the pressure distribution over the entire body, which is important for naval application. Because if you have adverse pressure distribution across the body, the sensors will be affected. The body will be creating noise. There will be vibration. If you have noise and vibration, it can be detected. And any naval platform or any naval vessel or any naval ship vehicle, which can be detected, it is of no use. So we need speed, that means speed of computing. For example, if we do 4 by 2, we should get 2, and we should get 2 as fast. Now, we will not use calculator if it takes 1 hour. Similarly, the field of hydrodynamic application, when you want to compute drag, when you want to optimize drag. Now, over a period of time, issues are not really computing a particular characteristic. The issue has shifted from computing of a particular characteristic, hydrodynamic characteristic, to optimization of that characteristic within a particular set of requirements. Now that's where the complexity comes into picture. That's where the speed and memory comes into need for memory. Now, memory is important because numerical schemes are recursive. So I plus 1 is defined as I plus delta. So you start with I, that's called initial guess, and then you keep on repeating this for higher and higher values of I plus 1, I plus 1, 2, I plus 3, I plus 4. And then you see the difference between I plus j minus I plus j minus 1. And if the difference is getting smaller and smaller, then we say that it is approaching the convergence. And when the difference satisfies a particular requirement, it may be 10 to the power minus 3, it may be 10 to the power minus 4, depending upon what kind of application you have in mind. And then you will say that, okay, up to here it can be assumed to be converging. Now, we have simulations which tend to grow until they will be dominating, overwhelming available resources. For example, if I can simulate 1000 neurons, wouldn't it be better? Wouldn't it be cool if I could do it 2000, 10,000, 10 to the power 87? Now, in the field of hydrodynamics, it is important for us to understand that we should stop when we assume that a certain level of convergence is achieved. For example, flow over an aeroplane. Now, the classical aerodynamics state this very clearly that if a teraflop machine were available, still it would take around 200,000 years to solve a particular problem of flow defined over an aeroplane. Now, this means the resolving all the scales. That means removing the scale effect. So 1:1. Upright men 1.8 million years ago. Suppose there was a teraflop machine available. Then roughly we will be getting result right now. Now this tells you three things very specifically. One is that sometimes the problem definition itself will tell you that this problem cannot be solved using the existing computing mechanism. So these class of problems which are expected to take very long time, for example, problems related to optimization, problems related to flow defined over an aeroplane, reducing the effect of scaling, they will take so long time that you need to think beyond the traditional methods of computing. And that's where the quantum computing comes into picture. But that's not the focus of this lecture. Here the idea is to tell you that when you think of computing, when you think of scientific computing, first try to understand where you are applying, why you are applying, what is the significance of this, and can you really solve it within reasonable speed and reasonable memory. Optimization is important and it starts with optimizing the processor. The profile serial number is like one processor defined as a core, and it's where maximum time is consumed. Now, if processor is somewhere the maximum time is consumed, then the basic question is that can we speed it up? Can we think of algorithms which are faster? Can we optimize library? Can we reduce, eradicate, remove all the operations which are wasteful? Now, all of them have been inbuilt now into the processors which comes into your computing machine. They have been integrated with optimized library. They have AI application which is used to identify operations which are wasteful. They have been designed to automate algorithms on a faster speed. Now, the basic idea of parallelization, or when we say the parallel computing, is to think problem in terms of chunks, problem in terms of parts, problem which can be decomposed into different domains, and then solve a particular chunk on different processors. Now, every problem cannot be parallelized. Every algorithm of computing cannot be parallelized, especially if the operations are dependent on one another. But if the operations are independent on another, or if one doesn't depend upon another, in that case, it is easy for you to parallelize. Second issue comes in compiler. Compiler really doesn't complicate the algorithms. It is usually very friendly. Optimizers are quite refined. And nowadays, compilers are also optimized. They come with different levels: O1, O2, O3. As a rule of thumb, it is always important for you to check the level of optimization available in your compiler. And normally they will come with O3, but faster and faster versions are available, but they will be costly. For example, O5 is available, especially for C++ compilers. Pavatron, the Fortran versions, they are also available for 5. For C++, some of the companies, especially Silicon Graphics and all that, they also make 7. But normally, whatever you buy, Dell and all that, they will come with only O3. Lots of flags will be available, and many will be available for optimization. The good news is that many compilers, in fact, most of them, will automatically parallelize a shared memory system. Now, the bad news is this usually doesn't work well. Now, to understand this optimization level, O3, the compiler performs more extensive optimization than at O2. Optimization that require large amount of compilation time or space. And the idea is through implicit memory uses and the limits are eliminated. Now, this I just explained to you before. Libraries are an important source of time consumption. Solvers is often a major consumer of CPU time. And if you have more and more standard libraries inbuilt into it, in that case, the solver will actually take lesser and lesser time from the CPU, memory from the CPU. For example, all of you have read this book, Numerical Recipes in Fortran, in C, in C++. It's a very good book, but most of the algorithms which are given there, they are not optimal. Now, this is something also which we need to understand that when we define operation, we have to be very careful because definition of basic matrix operation itself adds to the complexity. All of us have some background in matrix analysis, matrix computation. As a rule of thumb, it is important for you to avoid inversion of a matrix. Do not rely on inversion of a matrix to solve any set of simultaneous equations. The method is very simple that you inverse it and you will get the solution, but that's not really the ideal way. It is a very complex way of getting roots of a simultaneous equation. The division operation should be used as little as possible. The matrix inversion, after that division, after that multiplication, after that the negative sign, and after that the addition. So they are the set of operations, mathematical operations, basic mathematical operations, the decreasing level of complexity. Similarly, whenever we write a code, it is important for us to check the level of accuracy we need. For example, should we stick to 10 to the power minus 2, 10 to the power minus 3, 4, 5, 6, 7? It is also important for us to know what is the reliability in computing we want. Because when you say your computing has to be reliable, and you have very little scope of unreliable computing. In that case, it will shift towards what we call interval arithmetic, rounded interval arithmetic. But also understand that any computation in rounded interval arithmetic is time consuming. It's very slow. Any computing with floating point arithmetic, with either single precision or double precision, is much less time, and double precision will give you sufficient accuracy. But it is not reliable. It has been proved quite extensively that even for simple cases it may fail. But the argument is slightly different that you don't have a choice except to go for rounded error arithmetic, which remains an active area of research. So if you Google rounded interval arithmetic, you will find that there's a group of people who has worked extensively on. So it has never been as popular as floating point arithmetic, but it was never dumped altogether. That means people kept on working on the concept of interval arithmetic, especially the company Sun Micro Systems. They have done pioneering work on that. IEEE also has a standard available for interval arithmetic. Some of the best institute in the world, especially MIT Design Laboratory, they have done extensive work on using rounded interval arithmetic, and they have developed a system by which you can compute root of a polynomial within a guaranteed accuracy, and that guaranteed accuracy is user defined. Now that's not possible with floating point arithmetic because it has inherent approximation. So it is important for you to know what is your boundary, what actually you are looking for, what actually you want. And within that particular set of requirement, you have to optimize your algorithm. You have to optimize your algorithm on the lowest complexity side as possible. LabLac is a set of libraries available. That's a good resource because most of the algorithms available there, most of the libraries available there, they have been optimized. Libraries are often available. They should be utilized, provided they have been optimized for the local architecture. The disadvantage is that they are not portable. That means when you try to develop a system which is modular in architecture, in that case, they may not be transferable from one architecture to another architecture. What is the beauty of parallelization? The idea is very simple: divide and conquer. By the way, this was also the policy of Britishers when they conquered India: divide and rule. That's what one of our leading light, Netaji Subhash Chandra Bose, wrote in the civil service examination when they asked him, what is the foreign policy of British in India? He just wrote divide and rule. So this idea is like something which has been used in many branches of engineering, especially in the field of computing. Divide and conquer. Divide operations which are repeatable, which are getting repeated among many processes. Perform operations simultaneously. Now, if a serial run takes, for example, 10 hours, and if we hit the problem with 5,000 processes, it should take about 7 seconds to complete. You can just check. So it looks very simple. The issue is that when it comes to implementation, it is not so easy. But still, when it comes to computing, and you really want to speed it up and you want to reduce the memory consumption, there are only few techniques which are available, and this is one of them. Now, that's what I was telling that it is not possible for you to get the problem defined in such a way that calculations are made independent of each other, especially in the field of numerical analysis. The whole thing is start with the initial guess, get the delta. Delta is coming from the derivatives, and then take the forward step or the backward step and take the next iteration and keep on repeating it. Or even if you remove the derivative side, go with the soft computing. Searches are random. Again, start with the initial guess, search for the next direction, get the next guess, take it, and keep on repeating it. Here also we need to understand that whatever comes from basic analysis, basic mathematical analysis, basic numerical analysis will guarantee you certain convergence. That the results are converging, the results are approaching to the desired accuracy. Especially the methods which are based upon gradient or the methods which are based upon derivative. Methods which are not based upon derivatives or which are typically coming from the soft computing side, they may give you the result, they may not give you the result. They may miss the local optimum, they may miss the local maximum. So it is not guaranteed that whatever they are computing, that is the global maxima or global minima or local maxima, local. What is the argument is that if we search sufficiently large domain in sufficiently large number of random directions, then the possibility of us getting the result right will be slightly higher. But there is no guarantee. On the other hand, when you go through the route of derivative, either by finite difference or by finite volume or by finite element, all of them are based upon the derivatives. All of them are based upon the gradient. Then you get answers which are accurate with the proven analysis. So we know what is the level of convergence, whether it is linear or quadratic or superlinear or cubic convergence. Also, it is important for us to note that further, if we say that the function which we are dealing with, because we are talking about optimization, it is important for us to know this. If we can show that a particular problem of optimization is a case of convex optimization, in that case, the local maxima becomes global maxima. Local minima becomes global minima. Now think about it. If you can prove that this is a problem of convex optimization, this is a problem of non-convex optimization, then you have that definition very right. That once you have the local, it will become global. This is not true when it goes to the non-convex optimization side. So in the field of optimization, this remains an active area of research, how to classify the problem into convex or non-convex optimization. And if you can check this, you can Google this, write the word convex optimization, and you will find that some of the leading researchers, especially from Stanford, they have done pioneering work on convex optimization. The professor name is Stephen Boyd. He works in Stanford. He is a professor of electrical engineering. This is important for you to know what problems are there in the field of convex optimization, what problems are not there, which cannot be classified as convex. Now, any problem of linear optimization is basically a problem of convex optimization. Now, because we are relying too much on recursive computations, they can't be performed simultaneously. Similarly, any problem which is tied with the time history, also cannot be parallelized. It is difficult for you to parallelize time evolution of a system. But to maximize amount of parallel code, it is very occasionally you will find it easy, but usually it will require a lot of groundwork, a lot of understanding, and this is important for you to understand very clearly. Methods which are used for parallelization will, of course, depend upon the hardware. For example, the first idea itself is how do you distribute the memory? How the memory is to be allocated. Now, this can be done provided each processor has its own space in the address. If one processor needs data from another processor, it must be explicitly passed, it must be programmed accordingly. You can also have shared memory, and we can have the temporary memory allocation. That's what is used as a pointer in C. They are basically based upon the concept of shared memory. Pointers are used for temporary memory allocation, and they can be called, they can be removed depending upon what is the requirement of the memory, whether it is temporarily or it is permanent. The shared memory has a common address space. And when you have common address space, that means you really don't need the passing of messages from one address to the other address. Now, for example, here we have shown three different ways by which memory allocations are used. One is distributed memory. So we have processor 0, processor 1, processor 2, processor 3. And in the field of computing, it is from 0 onwards. But that's not the case with others. Others start with 1. So memory allocation is 0 with processor 0, 1 with 1, 2 with 2, 3 with 3. Now, we can also have a complete common shared memory platform where processor 1, 0, 2, 3 all are using the same memory space. Or we can have mixed memory space allocation. That means memory 0 is utilized by processor 0 and 1. Memory 1 is utilized by processor 2 and 3. Now, problems which are typically falling under the space of complete parallelization will be using distributed memory. Problems which are more or less using the recursive numerical analysis driven approaches, they will be using shared memory. Methods which demand both, that means algorithms which can be parallelized completely, algorithms which are semi-parallelized, where the numerical analysis come into picture, they'll be using mixed memory. So all three have a particular specific range of application. But this is also, you must understand very clearly that in the field of engineering science, there is nothing which is true for all. Every engineering problem, especially every engineering problem which is solved using numerical mathematics or computational mathematics, is applicable to a very specific set of boundary conditions given. You change the boundary condition, the solution may change completely. For example, we may have partial differential equation, we may have ordinary differential equation, we may have stochastic differential equation. A method which works fine for ordinary differential equation will not work for partial differential equation. A method which works for partial differential equation will definitely not work with stochastic differential equation. In fact, all the methods which work very well for ordinary and partial differential equation, they never work for stochastic differential equation. So it is important for you to know what is the range of application of your numerical method which you are investigating or for which you are developing your own code. We are trying to make you understand that when you develop your own code, what are the issues you have to be careful? What are the issues which are important? Similarly, the major complexity in any engineering solution or any solution of an engineering problem is coming not because of the partial differential equation or stochastic differential equation or the ordinary differential. It is primarily coming from the boundary conditions on which you are solving. This also needs to be understood very clearly that complexities arise because of the boundary conditions, not because of the nature of the equation we are dealing. Some of the boundary conditions will give so much complexity that even a simple ordinary differential equation cannot be solved. Now, message passing interface MPI is used for both distributed and shared memory. It is portable. It is freely downloadable. That's the other advantage of this. So most of the leading institutes, most of the leading computing companies, they avoid this free of charge. Then there is open memory processor or open memory processing unit or open multiprocessing platform. Different versions are available by different organizations. It is valid only for shared memory. It is not supported by compilers. It is supported by most of the compilers, but not all the compilers. It is usually easier than message passing interface, and it can be implemented incrementally. Now, the advantage of OpenMP, that is Open Multiprocessing, is it's an application programming interface. It supports multi-platform shared memory multiprocessing programming, which is done in C, C++, Fortran. It has instructions, set architecture, and operating systems, including Solaris, HP, Linux, Unix, Windows. It consists of a set of computer directives, compiler directives, library routines, library subroutines, and the primary and secondary and tertiary environment variables that influence the runtime behavior. In the message passing interface, the computational domain is typically decomposed into regions. And these decomposed regions are assigned to a processor. And a separate copy of program runs on each processor. Now, this is something which has been done quite successfully in fluid mechanics. So, we'll show some example. For example, this. It's a flow or an aerofoil. Now, you have possibility of decomposing this into different domains. Then, whatever partial differential equation you want to solve, you solve that within that domain at each point. So, the first step is discretized domain, which is used to solve particular kind of flow problem. System of coupled partial differential equations to be solved at each point within the each domain. We can say, for example, this decompose into four domains, and this is up to the user. Normally, we see the requirements where the grid is fine, where the grid is coarse, where the grid is much closer to the body, where the grid is close to the tail or close to the nose, close to the surface, high pressure, low pressure, suction effect. But the primary concern is that decompose the problem for different processes and then solve coupled partial differential equation on each domain. Now it's it's very fine, but what is the next step? The next step is the point depends on each other. So you have I dependent on I minus 1, I dependent upon I plus 1. So depending upon what is the discretization scheme, what is the numerical differentiation scheme, central difference, forward difference, backward difference, you will have dependency of forward with the backward, backward with the forward, all kind of possibilities will be there. So points depend on adjacent points, and because of this, they must transfer the information after each iteration. So that is done with what is called explicit calls in the source code. You have to be very careful when you write the code. For example, this is the central difference scheme between 2 points, I plus 1 and I minus 1, and you are computing the derivative at I. Now, please note that this is one way to get the derivative, but this is not really the ideal way to get the derivative. When 2 points are given to you and you are computing the first derivative, it is important for you to ensure that you never use
Sir, sir, it is not visible, sir. Wait for few minutes. There is a network issue. Please wait for some time. Sir will join again.
Good evening to all of you. Extremely sorry. There was a power failure at my point. Can you hear me now?
Yes, sir.
So,
Yes, sir. It is visible, sir.
let's take the point where I was discussing. Ah, So I was trying to explain this that it is important for you to get the dependency right, especially because the discretized elements are always dependent upon the adjacent elements, points. Also important for you to know right in the beginning where to use center difference, where to use backward difference, where to use the forward difference. So from left to right, if we move, the left, suppose we say the boundary conditions are from left to right. In that case, in this direction, the first point onwards, it is important for you to use the forward difference. Only for the next, after that, it is better for you to shift to central difference. When you go to the right, it is important for you to take the backward difference approach. Always remember that when you have 2 points, it is better for you to use either forward difference or backward difference. When you have 3 points, it is important for you to use central difference. And that way, your accuracy will be slightly better. Why it is not advisable to use 2 point observations in central difference is that, for example, here, this and this can be same. And in that case, you will get the derivative which is zero. For example, if I plot a line from here to here and here to here, and if I say this is the positive x-axis, this is the negative x-axis, this is the positive y-axis, this is the negative y-axis. Now think about it, a function is behaving like a triangular domain. So from here to here and from here to here. So here, the value of function is zero. But here, the value of function is positive. The value of function is positive, even for the positive x and even for the negative x. Now, if you take the derivative, I minus 1, this is I plus 1, this is I. So you will not get proper derivative at I. You'll actually get, because these 2 points are same. So phi I plus 1 minus phi I minus 1, they will be the same result. So this is the point which is same, this is the point which is same. So never use central difference with two observations. That's not really advisable. So in the field of parallel computing and in the field of numerical analysis, we try to focus on these issues because in the long run, they affect the speed, they affect the accuracy, and they also affect the memory allocation. Now, what is the problem with message passage interface? It's not really the best way to pass message from one element to other element, one memory allocation to other memory allocation, because it reduces the return. That means the returns get diminishing over a period of time. Our idea in the numerical analysis and similarly in the parallel computing is to maximize the ratio of computing to communication. That means the communication should be low, computation should be high. The problem with MPI is that the communication is larger, the computation is lesser. So parallel speed up should actually improve what we call parallel efficiency. So for example, T1 by Tn. T is the time, N is the number of processes. So one time for n number of processes, and the neta will become T1 divided by n into Tn. And that's something which we must get into the parallel computing. That means when we parallelize it at 4, our efficiency should improve by 4. So if we are speeding them parallelly, it should result into parallel efficiency, which will not happen in NPI because the ratio of communication to computing is adverse. Now, this is a classic case which we have done. That's basically flow over a cylinder. See the ideal case and see the actual case. You have the velocity computing, number of processors. So, what we are trying to say here is that ideally, using this, we should get something like this. That means our performance should improve if we have 8 processors, 10 processors, 12 processors, but that's not really happen. That means it will not be a line. It is something of this nature, which means that improving or increasing the number of processors beyond a point really doesn't improve the efficiency. And thus it becomes asymptotic beyond 24, 32, 40. So after 20 or 24, when you divide it further across 30 processors or 40 processors, it really doesn't improve. That also is important for us to understand that because of the sharing process involved in the memory allocation, it is not really parallel in the linear fashion. It becomes parallel in the quadratic or some cases even the cubic. Again, the same. The efficiency it, it, it improves when we have parallel processors, but again it becomes asymptotic beyond 30, 40. It really doesn't change. Open multi processing. This is usually at loop level parallelization. For example, for I0, I less than n, you basically take I plus plus and do whatever stuff you want. So between I starting from 0 to I less than n, we repeat whatever multi-processing we want. An open multi-processing directive is placed in the source code and it is placed before the loop. That means the multi-processing is done before it enters into the loop. Assigns subset of loop indices to each processor. No message passing since each processor can see the whole domain. That's the advantage, the beauty of it. What cannot be guaranteed is the order of operations. That means if it has to follow a sequential set of operations, then that is something which cannot be guaranteed in open. In that case, it is better to go through MPI. This is a typical example. This is example how to do it wrongly, and this is how to do it correctly. Parallelize this loop on two processors, processor 1 and processor 0. So some are going on processor 0, some are going on processor 1. Hardware issues. The faster processor is always good. That sounds very interesting. But how you're able to access the memory, that is the big driver. So it is important for us to understand that it is not really the processor which is coming into picture in CFD simulation. It is how accurately, how fast you are able to capture the memory that is important. Cache is a critical element of memory system. Processors in general, most of the leading computing machines have processors which have internal parallelism, such as pipelines. and they have multiple add-on instructions, basically to ensure that. Cache is a small chunk of fast memory between the main memory and the registers. So you have the registry, then you have the primary cache, then you have the secondary cache, and then you have the main memory. So this is a small chunk of fast memory. That means memory which can be accessed very fast between the main memory and the registry. Now, what is important? Variables are moved from main memory to cache in lines. For example, L1 cache line, it defines the sizes on our machines. Optron blade cluster 64 bytes, Power 4 P series 128 bytes, PPC 440 Blue Zine 32 bytes, Pentium 3 Linux cluster 32 bytes. If variables are used repeatedly, then of course the code will run faster because from registry it is the closest location. You are not even approaching the main memory. So from main memory, the variables have been moved to cache. So if these variables are used too often, too repeatedly, in that case, the code will run very fast. And that will improve the computational efficiency. Now, the argument is that if that is the case, then why not move the whole main memory into the cache? Now, that is something which is not really doable because it is expensive in the first place. It generates heat, and that is something which was found because it was tried with a set of Cray computers. They had every memory allocated to cache. That means no main memory, just everything is after registries. Very fast access. The computer was getting so hot that they have to use liquid cooling system. And later on, it was decided that this is not the ideal way of memory allocation. Cache hit is something which is telling you how many times the cache memory is accessed. And that depends upon what is the variable in the cache. Cache miss means the required variable is not in cache. If cache is full, something else must be thrown out, sent back to main memory to make room for the variable which is being accessed frequently. We want to minimize the number of cache misses. We want to maximize the number of cache hits. That's the paradigm of parallel computing. Mini cache, hold two lines forward each, and this is a code which is run. I strictly speaking to 0, less than 10, recursively. This is the main memory allocation code. We will ignore I for simplicity. Need X0 not in cache. It is cache miss basically. Load line from the main memory into cache. Same. People who are trying to write their own code can refer to this. Another important thing is that the contiguous access is also very important. Now, in the C class of programming, that means C, C++, C prime, all of them have multi-dimensional array. And this multi-dimensional array is stored as A00. For example, here, A00, A01, A02. In Fortran, multi-dimensional array and MATLAB is stored the opposite way. That means A11, A21, A31. There's a difference between C family and the Fortran and MATLAB family. Now, always order your loops appropriately. For example, in C, it is 0, the starting point. In Fortran, it is 1, the starting point. Similarly, in MATLAB, so it is important for you to loop correctly, appropriately. The P series, which we were discussing, is based upon shared memory. Where it is done, IBM Power 4 processors, 32 kilobyte L1 cache given is processor, 1.41 MB megabyte L2 cache per pair of processors, 128 MB L3 cache per 8 processors. That's how the shared memory is there in P series. This is the machine, the processing speed, number of processors, the memory allocation. So kite, pogo, frisbee, domino, twister, scrabble, marbles, crayon, light bright, hot wheels. Blue Gene, another class of distributed memory processors, 2048 processors, 1024 into 2 processor nodes. It comes in IBM Power PC for 40 processors, 700 megahertz, 512 megabyte memory per node for 2 processors. And then the cache is given L1 32 KB, L2 2 MB, 4 MB, L3. Blue Center, hybrid memory allocation, 56 processors, 14 into 4 processor nodes, AMD Optane processors, 2.6 gigahertz, 8 GB memory per node for 4 processors. Each node had a shared memory. Cache memory L1 64 KB, 1 MB, L2. Linux cluster, hybrid memory 104, Intel, GB, cache is also given. So this is the end of first part. Now I will briefly discuss the second part of it. If you have any question, you can ask me.
Any questions from the participants? You can please interact with sir.
Now this is what I was talking in the beginning, that it is important for us to understand that apart from the field of fluid dynamics, fluid mechanics, the high performance computing is important in many areas of application. In fact, in some of the areas, it has been very successful. And from there only, it has come into fluid mechanics, fluid dynamics. In general, the problem of fluid dynamics get complicated because of the sheer size of the body, the velocity, the flow separation, formation of vortices, pressure distribution variation, and all of them play a very critical role in understanding the flow over the body. For example, yesterday we were discussing about underwater vehicles. So take the case of drag, because drag is dominated by the viscosity. And because of this, it is important for you to solve the Navier-Stokes equation. So high performance computing is needed. On the other hand, if you are designing a propeller, Laplace equation, they are non-viscosity dominating. Thrust anyway is not coming because of viscosity. So you don't really need that much high performance computing. So parallel method will work very fine for thrust delivered by a propeller, added mass, All of them are not driven by viscosity. So the drag will have two components majorly. One is dependent upon the Reynolds sum and the skin friction, the frictional drag. The second is coming because of the viscous pressure drag. And that drag is actually dominated by the shape. So if you have a body which is giving you a surface area S, you have a Reynolds number, you get the frictional coefficient, and you can compute the skin friction drag on the body. The same body within the same surface area, when it is faired differently, can give you completely different viscous pressure drag. So in the drag, you have one component which is coming because of the total size of the body, the surface area, the friction. The second is coming because how the pressure is varying over the body. So how the body is paired, how the nose is paired with the middle body, how the middle body is paired with the tail. So these are important issues when you minimize the drag. And that's where major research has gone into how to reduce drag on vehicles running in air, running in water, running in the interface of air and water. For example, ship, it runs at the interface of air and water. So we started our lecture on this that theory and experiment have been two traditional pillars of scientific research. So you have theory which is coming because of the maths, because of physics, because of the chemistry, basically the science. Then experimental mechanics, that means can you make the model? Can you run it? That's the experimental side. Now, suppose there's a mismatch between the two. Either theory is not valid or the experiment is not valid, or theory is incomplete, theory is too expensive, too limited, experiment is too expensive, too time consuming. In that case, the focus shifted from theory and experiment to what is called simulation. Simulation based design, simulation based engineering that has been a dominating factor in all the major branches of engineering for the last 30, 40 years, especially after the advancement of computing power. Very large system integrations have been done very successfully with high performance computing. And that is the first area where high performance computing has been phenomenally successful. Very large system integration. Abstraction layers are missing, and that's where the high performance computing comes into picture. Now, non-linearity is one issue in engineering. I explained to you that you may have case of convex optimization, you may have a case of non-convex optimization. In convex optimization, it is easy for you to ensure that once a minima or maxima is computed, then it's global or local. There is no difference. So once you get it, it becomes global. It is not true when it is problem of non-convex optimization. Similarly, a non-linear programming gives rise to non-convex optimization. Similarly, the quantum mechanics doesn't really allow you to solve any problems. But if it allows you to solve the problem, then there will be actual reduction in the complexity. And that is the reason why a lot of research has gone into building quantum computers. Because quantum computers will essentially reduce the complexity, which is not happening when you are using high performance computing. High performance computing is giving you computing power. It is giving you lesser computing time. It is also giving you large memory allocation. But that's not really reducing the complexity of your problem. In quantum computing, the complexity of the problem itself will reduce. So the NP hard problem will actually not be NP hard. So because of these two issues, there is no escape from high performance computing. Now, what are the areas, major areas of application? Fluid dynamics, aerospace. We just discussed one, domain decomposition for flow on an aerofoil. Automobiles, the high class automobile of less drag, high comfort, lower CG. Chemical and power plant. Structural mechanics, crash simulation. Nowadays, it is very important for you to design a car which is crash worthy, design a automobile which is crash worthy, design a submarine which is crash worthy, design a ship which is crash worthy because of the security environment. So people can fire torpedo, people can fire missile, and that will give you impact, and that impact will allow you to get into crash mechanism. So crash simulation is a area which is extremely important and also extremely time consuming because you have an impact which is happening over a short period of time but with very peak magnitude. Armor design because of the security environment. So you have armors designed against bullets, against bombs, against explosion, against fire, and all of them are computationally expensive problems. Signal processing used in the field of oil exploration, astronomy, multimedia data mining. Then you have quantum mechanics, nanotechnology, computational biology, medical diagnostics. All of them have some potential application of high performance computing. Now, what is the computing crisis? And why have we come to this level that we are talking about high performance computing? And what is important for a country like India to get into this field? Now, one is that we are slightly better in coding, assuming that we are good in numbers. And if we are good in numbers, that means we are good in logical thinking. And if you start teaching computer science from a right the sixth onwards or eighth onwards, they will have a logical way of thinking. And when you have a logical way of thinking, it is helpful for you to be a good programmer. So, keeping that in mind, this is an opportunity for India without a choice. Because all the fields, for example, naval construction, the drag, structural mechanics, crashworthiness, all of them are the areas where you have some Indian companies active in design. So, because of this, we have started advocating that the high performance computing course should be made basic for all graduate and postgraduate students. Furthermore, we can note very specifically that processors are not getting any faster. They are being optimized, but they are not being made faster and faster because there are issues when it comes to speed. Hence, you have proliferation of multi-crores, many industries, claiming that this is the optimized processor, O3, O5, O7, O9, like that. But essentially, the speed is not getting up, or the speed is not improving the way it should happen. Computation and communication. This is something which I discussed when we were talking about memory allocation. Our idea in the field of computing is to maximize on computation, minimize on communication. And normally in the field of computer science, especially when it comes to processors and all that, still it is lot about communication, less about computation. So there is speed mismatch. And this speed mismatch can be because of processor, it can be because of server, it can be because of cluster levels, it can be because of so many issues. And what to do with so many crores anyway? The why billions of dollars is being put into this industry is that there's a potential market. So there's opportunity. There's a need to program correctly to capitalize on all this investment. And that remains a challenge. So our idea, our focus at IIT Madras is that high performance computing should be democratized. That means it should be made, at least the basic should be made available to the graduate and undergraduate students. And it should be mainstream. That means everybody should know what is high performance computing. And it's not really that complicated. Now, what is important to start with? It is important to start with complexity. How do you handle complexity? This is something which I briefly talked about. When you write your code, when you write your algorithms, be careful. Do not rely on operations which are highly complex. Rely on operations, rely on techniques which are much less complex. For example, all the decomposition, LU decomposition, lower triangular, upper triangular, they are always much less complex than inversion of a matrix. Computing the derivatives. There are other ways by which the derivatives can be computed rather than taking the gradient. Limitation of the human mind, lemmas leading to theorems, clocking abstraction, there's synchronization effect, and decoupling of concepts. Now, if you can decouple the partial differential equation, then they can be reduced to ordinary differential equation. Solution of an ordinary differential equation can be done by what is called shooting method, which is much more simple. But if it is not, in that case, it becomes a boundary value problem. So our idea should be to see if a partial differential equation can be decoupled into ordinary differential equation. Can the ordinary differential equation be solved with initial value problem rather than boundary value problem? Because solving initial value problem is much less complex than solving a boundary value problem. Solving a coupled partial differential equation is much costlier in terms of computing power than decoupled ordinary differential equation. Need to break them for efficiency. That's what I am saying, that the computational efficiency will improve when you decouple them, when you reduce them from PD to OD, and in OD when you reduce them from boundary value problem to initial. This breaking needs to be creative, selective. Otherwise, you will not get any improvement. You will get only chaos. Once done properly, it will lead to, or it may lead to, a better abstraction. Abstraction example, for example, in case of physics and chemistry, quantum mechanics, continuum mechanics. computing task, polygons, transistors, gates, register, ISP. The communication, stack, memory, hierarchy, cache. So you have registry, primary cache, secondary cache, main memory. You can also introduce the concept of virtual memory. You can have structures which are highly organized, structures which are highly hierarchical, depending upon what kind of computing we want. Now, what should be our idea? How we should go? Layout design, diffraction should be attempted because rectangles get fuzzy. Now, this has importance in the field of structural mechanics. You have two major class of elements. One is triangular based and another is rectangle based. The triangular based elements are preferred because they can represent any arbitrary shape, but they are also not suitable for a class of problems. For example, buckling. A triangular element will not be suitable for buckling. A 32 node or 64 node rectangular element will be suitable for buckling, but it may not represent any arbitrary shape. Similarly, think of circuit design. People who are coming from electrical engineering background will know that all transistors are not the same. Logic design, the wire delay can actually dominate the switching delay. The processor design, clocking can hit the wall, it can skew and power the processor design. Softwares, when you design them, they need abstract model of processor, memory, and interconnect. Now, today we discussed about the parallelization. That means, can you solve problem or part of the problem, assuming that the domain is decomposed into n, and decomposed domains are solved on different processors. They can be mixed, they can be shared, they can be non-shared. That means a specific memory for a specific processor. The idea is that when you decompose into domain, what are the domains where the solution accuracy is needed on the higher side? What are the areas where you don't need solution accuracy on the higher side? So this is important because the more solution accuracy you want, the higher will be your number of element required. So people who are doing CFD, they will know that the grid is a very important. And when you say grid, then it is important for you to do grids at different scales, finer, coarser. In the case of grid, you do the grid independence study, grid convergence study, all to know whether the grid will actually converge or whether it will properly represent the shape or not. Normally, when it comes to close to the body, the grid is finer. When you move away from the body, the grid gets coarser and coarser. In CFD, the the termination criteria or up to what size or up to what domain we are looking for the solution. That is also important and it comes purely from the empirical understanding. So if the diameter of the body is D, they say that up to 3D or 5D or 0.1D or 0.2D, depending upon that. So a lot of termination criteria, a lot of input comes from the empirical understanding which has been developed over a long period of time. So we cannot make the mistake of saying that CFD or numerical simulation or numerical modeling is independent of the empirical understanding. No, especially when it comes to the fluid flow problem. A lot of termination criteria, a lot of equations are there which are coming from the empirical understanding or empirical modeling, which are used in CFD. Computing how to balance between correctness and performance. Now, from the mathematical side, I told that it is important for you to see what is the difference between I plus 1 minus I. That means, are you getting two successive values which are close? And when the difference starts getting closer and closer, people say that the results are converging. Now, it happens in CFD, it happens in all the numerical modeling. The initial first few computations will give you results which are haywire. And then slowly, it will start getting converged. So, this issue of convergence is true for both sequential and parallel programming. That means whether you do I plus 1 equal to I plus delta, or you have I plus 1, I plus 2, I plus 3 being computed on different processors parallelly. This correctness, that whether you are getting values which are close and whether you are transferring the values correctly, that is important. Efficiency issues, optimizing compilers, most of them nowadays come with some kind of optimization, but that is largely confined to sequential programming. That is not confined to parallel programming, and that is not suitable for high performance computing. Algorithms, people focused primarily on order of magnitude analysis, which is not really the ideal way of making the analysis. It makes the Turing machine suitable. And this is what I told you, that there are only 4 or 5 basic mathematical operations. So finally, whatever you do, it will be reduced to these 4 mathematical operations. So modeling and simulation finally can be done by a Turing machine. The only thing is that it will take much longer time. But the idea is very simple, that any mathematical algorithm will finally be reduced to basic mathematical operations: addition, division, subtraction, like that. Hardware, we have discussed this before. We need a realistic abstraction of the hardware, and it must need the problem abstraction. Processor need to model the pipeline, and this we also discussed that some of them are coming with the pipeline. Memory need to model the access timing, how fast you are able to access the memory. Access the pattern dependent, again throughput versus latency. Random access memory is not exactly random access. Cache transparency is a performance problem. Cache coherence is also yet another problem. Now, this is something which I told you in the beginning, that this is advisable for you to keep all the variables which are accessed as frequently as possible in the cache memory. If it is not there, it is cache miss. If it is there, it is cache hit. So the idea is to maximize on cache hit and minimize on cache miss. But that's not really simple. That's what I said, that high performance computing need some critical input from you to make the problem applicable towards any of the tool for high performance computing. Need to model inter-processor communication, for example, between blades on a cluster, between dies on a blade, between cores on a die. Physical interconnect delays the whole computing power. Interconnect topologies are being researched. Interconnect protocols, retransmission, etc. Now, even on a chip, it is there, it is available. The productivity challenge, the programmer need to learn the new performance aware models. Now, that is something which we have started in our institute, that when we teach programming, we also teach what is important for you to know before you write your own code. Programs must match the models which are available or the understanding which is available. For example, they are not just Turing machine equivalents. They are not even idealized parallel computing machines. That means it is better for you to think beyond parallel computing, beyond numerical mathematics, and try to capitalize on all these concepts. Now, in the case of high performance computing, what is the ideal phase one? The ideal phase one is write programs which are parallel and which are parallel for idealized parallel machines. Then map these programs onto real architecture. That is machine dependent optimization. What kind of machine you have? Possible, or at least partially automate mapping. That means depending upon what kind of compiler you have, what kind of CPU you have, some kind of automated mapping is possible. Phase two, develop algorithms for real models. Application perspective, ideal programming paradigms are application domain dependent. Most architecture mapping problems are best solved by exploiting application characteristics. Black magic is basically to put everything into the mind of graduates. And they should be able to understand the methodology. And to understand the methodology, education in training is the key. Methodology should allow them to graduate to automation, automating use of libraries, parallelizing compilers for real machine models. Why it is important for India? Dropping hardware costs will drop significantly over a period of time. And this will give rise to the people who can solve real world problems on available hardware. We have large workforce that is adept, that is good at programming. But we also have a challenge that education for the new world of performance driven parallel computing is something which is missing, which is just coming up, which gives that is it better to have a program or a course or a short term course on computational science. Also, it is important for us to integrate Indian Institute of Science Education and Research, that kind of institutes, into the broader world of computing. Thank you. If you have any questions, you can ask. Any questions?
Yes, if there are any questions, please interact with sir.
Good evening, sir. This is Rakesh Kumar.
Yes, Rakesh, please.
Sir, actually, this presentation today is like related to scientific computing in general.
Yes.
It's too much content where only the person who worked or have more experience can capture what you're talking about. But I'm new to this field, so I would like to know, like, sir, the slide which you mentioned related to without parallelization and with parallelization. Like there is a code for I is equals to zero, I less than n, I plus plus. With parallelization, without parallelization, you have shown a slide, sir.
Yes,
Can you please explain, like, sir, for suppose there is a very simple code which you mentioned.
yes. What what we are trying to make everybody understand
Sir,
is,
sorry to interrupt you, sir. Like
yes, please.
I'm working in solid mechanics, sir. Like the code which I run in MATLAB,
Hmm.
it will take me around 17 to 18 hours.
Okay.
Just simple code for fracture simulation.
Hmm.
So I thought initially to parallelize it, but I have no idea how to do it. But many of the in research community who do a complex computational work in fracture, they do parallelization. They just write that word in their papers, like doing parallelization, and they
Yes.
will reduce the computational time, obviously computational cost. So, just can you give an insight so that maybe I
Yes.
will get curiosity about this parallelization concept so that I can work on it.
Yes. So what we need to understand when we try to analyze any, any program, what is the time domain? For example, I have shown one aerofoil and I have shown that this is the complete domain. And the complete domain can be decomposed into four domains, subdomains. And then each subdomain is solved on a particular processor. Now, in your problem, it is important for us to know what is the complete domain on which you are solving the problem of fracture mechanics. Whether that particular subdomain can be decomposed into other class of subdomains, 4, 5, 6, 7. That's not the issue. But is it possible? Second, once you do that, for example, if I say I starting with 0, and from 0, if I go to, for example, up to 10, then 0, 1, 2, 3, 4, 5, 6, up to 10 can be solved on a single processor. That's the classical approach of computing. Or 0, 2, 4, 6, 8, 10 are solved on 1. 1, 3, 5, 7, 9 are solved on 1. That's the way you split the domain. Now the issue is that when you compute 0, the 0 will go as an input for 1. What you compute at 1 will go as input to 2. That's how the discretized domain works. So when you parallelize, it is important for you to share and pass this message through what is called NPI. That's what we were discussing about. That how 0 will go to 1, how 1 will go to 2, but 0 and 2 are computed on one particular processor. 1, 3, 5, 7, 9 are computed on another. But one will have input from 0. One will give output which is input to 2. So when you program it in the loop, that is something which you have to be very careful. Once you do that, then you will be able to parallelize. Now, in general, when we generate a grid, when we generate the elements, we ensure node to node connectivity. That's what we do in finite element analysis. What is needed here is that apart from node to node connectivity, how one particular element is providing the output which is used as input to the element which is adjacent to it. Once you are able to do that, then only you can parallelize. Now, it may be possible, depending upon the kind of problem you have, that you cannot solve two unless until you are able to solve one. You cannot solve one unless until you are able to solve zero. Now, in that case, you cannot parallelize. because in that case, it's a classical problem of sequential program. That means you cannot solve 10 unless until you solve 9.
Okay, sir, understood, sir.
So,
Sir, like,
know the catch line. But understand this very clearly that it is possible within certain loss of accuracy that most of the problems, even of sequential programming, can be done with parallel programming. Now, coming back to your first question, that because it's too technical. See, if I say that I'm using high performance computing for flow over an aerofoil or crash worthiness and all of that, I can discuss the application. That's one aspect of it. But unless until you know what is the issue in parallelization, what is high performance computing, the application really doesn't serve the purpose. Now, that is the problem why high performance computing has never taken off in India in a large way. Because people will say, okay, this problem can be solved with high performance computing, but what actually is high performance computing? That is something which is not taught. That is not something which is like available in terms of short term course or whatever courses we are doing. So, unless until we get this bottleneck cleared, the high performance computing or parallel computing will remain in a very kind of specialized application domain in one or two institute here and there. That is something which we are trying to address from our side, that let's create a platform on which at least we start teaching them how to parallelize, how to do the message interface, how these issues are tackled, so that once they have these ideas very clear, then it is easy for us to tell them, okay, now take this problem, take the domain, divide it into 4 subdomains, and then just do the parallelization. Anything else?
thank you, sir. Sir, can I ask you a simple question, sir, which I thought maybe can be parallelized? For suppose, if there is a finite element, sir, in
Sure,
that finite element, if we have 4 Gauss points,
sure,
so each Gauss point, the MATLAB will compute the physical modeling aspect. Can I parallelize, like one Gauss point is given to one processor, like that 4 Gauss points are given to 4 processors, where I can collect all Gauss points solutions to one platform, and I can run the next computational work. Can I
sure,
do it, sir?
sure.
Okay, sir.
All these softwares which you are talking about, MATLAB, Mathematica, Apple, they have some scope for parallel computing. It is available in them. Unless until you have a very specific requirement that I plus 1 depend upon I, and it's a typical case of sequential programming, most of the problems can be parallelized. The only issue is that element to element connectivity and how the displacement, how the deformation, or in the case of fluid mechanics, how the velocity and acceleration is transferred. That is something which is important, which need to be understood in a very kind of detailed manner. Similarly, what is the final equation being solved? Can it be decoupled? Can we reduce from OD to, sorry, from PD to OD? Because initial value problems are the most ideal one to be parallelized. Then comes the boundary value problem, then comes the other higher steps. That's what we said, that in the case of coupled partial differential equation, the first issue is that you have to explore whether they can be decoupled. You cannot have a coupled partial differential equation which can be solved on a parallel computing machine. It's practically impossible, because the coupling will mean that one input goes to the other goes to the someone else, and in that case it becomes very complicated. And understand that the idea in computing is to reduce the communication, increase the computation. If the communication itself is consuming time, then whatever parallel computing you do, the efficiency will not improve. The more communication you have between the elements, between the panels, between the grids, the whole thing will come back to the previous one. That means ordinary.
Okay. Got it, sir. Thank you very much.
Anything else?
Any questions from the audience? Sir, we can close the session, sir.
Okay, thank you.
Sir, thanks a lot, sir. Thank you for
Thank you,
joining,
sir.
It's our responsibility to help our students, our fellow colleagues, our teachers. Wish you all the best. Thank you.
Thank you, sir. Thanks a lot, sir. Thank you, Swami. Thank you, Sairam, for
Thank you, sir.
conducting the session successfully. Thank you.